In this lesson, we're going to examine a different kind of pattern of numbers. There's lots of things that don't fit nicely into arithmetic or geometric, but still have patterns. One of these, for example, 1, 1, 2, 3, 5, 8, 13, is called Fibonacci sequence. And what happens there is you take your two previous numbers and add them together to get the next number. 1 plus 1 is 2. 1 plus 2 makes 3. 2 plus 3 makes 5, and so on and so on. That wouldn't fit into arithmetic or geometric because there's not a constant difference. Another powerful set of numbers is something called Pascal's triangle. The way Pascal's triangle works is it makes an array of numbers in a triangle shape. And the way you figure out the numbers in the next row of the triangle is you add the two numbers directly above it to get a new term. So we always start with a 1, and we end with a 1, because the only thing directly above it is the number 1. But for every other term, 1 plus 2 makes 3. 2 plus 1 makes 3. So my next one will be 1 plus 3 makes 4. 3 plus 3 makes 6. 3 plus 1 makes 4, end with a 1. If I did another row, I'd have 1. 1 and 4 makes 5. 4 and 6 makes 10. 6 and 4 makes 10. 4 and 1 makes 5, and 1. And there's some symmetry to this, if you notice. Because we're adding the same numbers together in one direction, then back down the other direction, we often end with the same numbers on either end of the row. There's tons and tons of patterns that exist within Pascal's triangle. Okay, for example, one of them, the sum of each row of Pascal's triangle equals 2 to the n, where n is the row number. So we go back for a second here. Okay, notice we call this row 0 the starting row, okay? Row 0 has a total of 1 in it. Well, 2 to the power of 0 equals 1. Row 1 is 1 plus 1 makes 2. And 2 to the 1 comes out to 2. Row 2, 2 squared. 1 plus 1 makes 4. Hey, it works. We can even skip down a few. 2 to the 5 should be row 5. Now if we add up 1, 5, 10, 10, 5, 1, we get 32, which is exactly what that row adds up to. So that's one nice little thing. You can add things up. Based on that, we can problem solve. Which row adds to 1024? So 2 to the what makes 1024? Well, a little bit of guess and check, which we're kind of familiar with now, will tell us that the 10th row comes out to 1024. So that's one nice little pattern in it. Okay. We also like it because we can use it to solve problems, in particular, path problems. That is a path where you have a starting point and an ending point, and you have to get from one to the other in the most direct way that you can. Okay, so for example, I want to spell the word math. Well, to spell the word math, I have to start with an M, then go to an A, then to a T, then to an H. Okay. So if I say my starting point is right here at the M, there's one way to start there. I have one way to go to this A, or one way to this A. I can go this way, or I can go this way. After I go MA, I can go to this T, or I can go to this T, following the path. I can't jump to the far T, okay? I can go to this T or this T. And then from there I can go to H, or H, H, or H, H, or H. Those are all my paths. Well, if you fill in the numbers of how many paths we have to get to each letter, it kind of looks like Pascal's triangle. Okay? And these are threes here in the middle, because there's one path from this T and two paths from this T, which makes a total of 3 paths. So how many different ways can we spell math altogether? Well, the rule is the sum of the values at the end is your total number of paths. In other words, 1 plus 3 plus 3 plus 1 gives us 8 different paths to spell the word math. Kind of cool. Okay. We can try another one. We want to spell Maclean's this time. So based on Pascal's triangle, I got one way to start the M. I have to go to the A's. I then have to go to the C's, either this direction or this direction. So I've got 2 different ways. To get to the L next, well, I only have the one path from C, but initially there were 2 paths to get there. So this number has to be a 2. right? It could have been MACL or MAC. There's two different ways of getting there. Same with this L, which makes these E's 2's now, and these A's 2 now. So instead of being 1's on the edges, we have 2's on the edges now. To get to the E in the middle, I have 2 plus 2, which makes 4. To get to this A, 2 plus 4 makes 6. Same thing over here. To get to the N, 2 plus 6 makes 8. 6 and 6 makes 12. 6 and 2 makes 8. To get to the S, I've got 8 and 12, which makes 20. And same thing over here, also 20. So total paths equals 40. 20 and 20. And I've got 40 different ways I can spell McLean's by following those paths. We've got some word problems. What else do we got? We got some shape problems. I want to get from A to B. If you think of these as north and east and south and west blocks, the most direct way to get from A to B, I'd have to go this way and then down, then this way, then down. But that's only one path. I could have gone here, and then here, then here, then here. I could have gone this way and then across. Oops, not there. I have to look on the roads, right? Here, then here. That's another path. How many different paths are there? Assuming we can't go round and round in circles, and why would you want to do that if you're trying to get from A to B? We can think of Pascal's triangle again. If I start at A, I have a single starting spot. I can go one different way to get to that corner, and that corner, and that corner, and that corner. And same thing with these corners. But to get to these inside corners, I've got different paths. 1 plus 1 makes 2. 2 plus 1 makes 3. 4, 5. If we do the next row, we have 3, 6, because I've got 3 plus 3, 10, 15. If I go this way or this way, I've got 4, 10, 20, 35. And then here I got 5, 15, 35, 70. 35s are going to go all the way along this way, right? Because that's the only way I can go along there. So I've got 35 for each one of these corners. And 70s all the way down the side here. But again, all the inside ones I have to add. 70 and 35 is 105. Plus 35 makes 140. Plus 35 is 175. 210. Next row, 175, 315, 490, and 700. Next row, 245, 560, 1010, 1710. And then the last row, 315, 975, 1985, and add that together and we'll get 3,695 paths from A to B. Okay. By doing Pascal's triangle, rather than having to actually go through and add them all up or draw all the different paths, which would be kind of difficult, right? Okay, that's what gives Pascal's triangle to solve some problems. That's the end. Today's homework is a handout. Okay, so print the handout off, give it a try, see what you can do. Just some simple things, finding some patterns, filling in Pascal's triangle, and solving some simple little problems there with paths.